You know, we all hear about the universe's ultimate speed limit, right? The speed of light. But have you ever stopped to think about the complete opposite? Is there a limit to how slow something can get? How perfectly, absolutely still it can be? Well, that's exactly what this is about, a journey to find the rock bottom of temperature itself.
It sounds like such a simple question, doesn't it? How cold can it get? But the answer? Oh man, the answer takes us right to the very edge of reality. It's this place where the physics we know and see every day just smacks right into the bizarre, mind-bending rules of the quantum world. This isn't just about a cold day. It's about finding one of the fundamental boundaries of our entire cosmos.
And this is our destination, absolute zero. We're talking 0 Kelvin. That's a bone-chilling minus 273.15 degrees Celsius. In theory, at this temperature, all that jiggling and vibrating that molecules do, what we call heat, it should just stop. Completely. It's the point of perfect, total stillness. Or is it?
All right, so here's our game plan. First, we're going to explore this idea of the ultimate cold. Then, we'll check out nature's coldest corners. After that, we dive into the human racing to absolute zero. We'll hit the quantum barrier, the thing that stops us. And finally, we'll get into why the chase matters so much.
Okay, so the first thing you have to wrap your head around is that absolute zero isn't really a place you can, get to. It's more like the horizon. You can walk towards it forever, but you'll never actually reach it. The laws of thermodynamics basically say it's impossible. Why? Well, because the colder you make something, the harder and harder it gets to pull out that next little bit of heat. To actually hit zero would take literally an infinite number of steps.
So, if it's an impossible goal, how close does nature itself get? I mean, the universe has had 13.8 billion years to cool down. You'd think there'd be some seriously frosty places out there.
And whoa, this chart really puts it all into perspective. Just floating in deep space, you're looking at about 2.7 Kelvin, thanks to the leftover heat from the Big Bang. The coldest natural spot we know of, the Boomerang Nebula, is about 1 Kelvin. But then, look at that last bar. That's us. Here on Earth, 38 picokelvin. That's trillionths of a degree above absolute zero. We didn't just catch up to nature, we've completely blown past it. It's incredible.
So you might be wondering, why can't nature get any colder? Well, it's because the entire universe is basically swimming in the faint warmth left over from its own birth. That's the cosmic microwave background. It acts like a giant universal space heater that's always on, just a tiny bit. It puts a hard floor on how cold things can naturally get. There's just no escaping it out there.
And that is where we come in. To get colder than the universe itself, we have to be clever. We have to build these insanely sophisticated shields and refrigerators to protect atoms from that cosmic warmth, and then actively suck the energy out of them. It's kicked off this amazing scientific race to the very bottom of the thermometer.
And the progress has been absolutely wild. Back in 1995, we created a whole new state of matter called a Bose-Einstein condensate, where atoms get so cold they basically merge into one giant quantum wave. Fast forward to 2021, and we set that new record in space, 38 picokelvin. And that quest, it's happening right now, as we speak, up on the International Space Station in NASA's Cold Atom Lab.
So how on earth do they do it? It's this beautiful three-step process. First, they use lasers. The little particles of light, photons, literally act like brakes, hitting the atoms and slowing them way, way down. Then, they use powerful magnetic fields to trap those super-chilled atoms in one place. But for that final push to get insanely cold, they do something that's perfectly described by this idea. It's called evaporative cooling. They gently lower the walls of that magnetic trap, which lets the hottest, most energetic atoms just fly away. And as they leave, the average temperature of all the atoms left behind just plummets. It's the exact same reason your coffee cools down as steam rises off of it. Genius, right?
Okay, so we're getting ridiculously close. Trillionth of a degree away. You'd think we could just take that one last little step, right? Well, no. Because right as we get to the finish line, the universe completely changes the rules of the game. We slam headfirst into a quantum barrier.
And here it is. This is the heart of the problem. On the left, you see our everyday classical idea. At absolute zero, things stop moving. Simple. But on the right, that's quantum reality. And it has a really weird rule. Particles are never allowed to be perfectly still. They always have to keep a tiny, irreducible amount of energy. This little bit of leftover motion is called zero-point energy. And let's be clear, this isn't a technical glitch we can engineer our way around. It's a fundamental property of the universe. It's a tiny quiver of motion that quantum mechanics literally demands every particle has, even at the coldest possible temperature. The why behind all this comes from one of the absolute pillars of quantum physics, the Heisenberg uncertainty principle. Think of it as a fundamental cosmic trade-off. You can know exactly where a particle is, or you can know exactly how fast it's going, but you can never, ever know both perfectly at the same time. If a particle were perfectly still, its momentum would be exactly zero. But the uncertainty principle says that if you know the momentum that precisely, its position would become infinitely uncertain. It would be everywhere in the universe at once. And the universe just doesn't work that way.
And really, that's the bottom line. It's a cosmic law, not a friendly suggestion. The universe has a minimum speed limit woven right into the fabric of reality. Perfect stillness is, and always will be, forbidden. So if we can never actually get there, what's the point? Why go through all this trouble for an impossible race? Well, because it turns out the real prize isn't reaching the finish line. It's everything we discover trying to get there. You see, when you push matter down to these ultra-cold extremes, it starts to reveal its hidden quantum self. This is the world where next-generation quantum computers will live. It's where we discover materials with zero electrical resistance, superconductors. It's where these bizarre new states of matter, like those Bose-Einstein condensates, suddenly appear. We can even use these systems to simulate the fundamental physics of the universe right here in a lab.
So the big takeaway is this. Chasing an impossible goal forces us to be incredibly creative. The technologies we have to invent and the deep secrets about reality that we uncover along the way, that's the real treasure. The quest for absolute zero isn't a story about failing to arrive. It's a story about the incredible triumph of discovery.
And that leaves us with a pretty cool final thought. The universe has hard rules, and some limits are truly absolute. Perfect stillness is one of them. It just makes you wonder, what other impossible things are out there that the universe forbids? And what will we discover by trying to do them anyway?